The night of March 22nd, 1945. Along a moonlit stretch of the Rhine River near the German town of Oppenheim, Obergefreiter Klaus Hartmann crouched in his foxhole, scanning the western bank through the darkness. He'd been told to watch for American bridging equipment, the massive steel contraptions that would take days to assemble. His orders were clear. Report any sign of pontoon columns, those long convoys of heavy trucks hauling solid metal floats that the Americans would need to span the sacred river. But Hartmann wasn't worried. The Rhine was over 300 meters wide here, with currents running swift and cold from the spring melt. Every German soldier had been taught the same lesson since childhood. The Rhine was Germany's greatest natural fortress, unconquerable without bridges. And bridges took time. Time the Americans didn't have, not with every German gun along the eastern bank already aimed at the likely crossing points. What Hartmann didn't, what German intelligence had catastrophically failed to understand, was that at that very moment, less than 2 kilometers away, American engineers were unloading something the Germans had seen before but never taken seriously. They weren't steel. They weren't even rigid. They were rubber. Massive, inflatable pontoons that could be rolled up, transported by ordinary trucks, and assembled with shocking speed. The Germans had dismissed them in intelligence reports as emergency equipment, suitable perhaps for small streams, but utterly inadequate for a river as mighty as the Rhine. They called them pneumatic floats, and in less than 11 hours, they would carry an entire American army across Germany's last natural barrier, shattering not just a defensive line, but 2,000 years of military certainty. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. For the men of the 249th Engineer Combat Battalion, the Rhine crossing had been weeks in preparation. But for the German High Command, it represented an inconceivable nightmare that they'd assured themselves could never happen. Their failure began not on the riverbank, but in the sterile offices of military intelligence, where analysts had fundamentally misread American engineering philosophy. The reports had come in from France and Belgium throughout late 1944 and early 1945. American engineers were using inflatable rubber pontoons, massive sausage-shaped floats that supported temporary bridges. Wehrmacht intelligence officers, steeped in a tradition of precisely engineered steel pontoons and beautifully crafted bridging equipment, filed these reports away with barely concealed contempt. The consensus was clear. These were makeshift devices, proof of American industrial improvisation, but hardly suitable for serious military operations. One captured, German intelligence summary, recovered after the war, described the American M2 treadway system as pneumatisch not behelf, emergency pneumatic expedients, suitable only for minor water obstacles. The report noted that the inflatable components appeared fragile, vulnerable to small arms fire, and incapable of supporting heavy military traffic for extended periods. What the Germans never grasped was that this supposed weakness was actually the system's greatest strength. The M2 treadway bridge system was a marvel of practical American engineering. At its heart were pneumatic floats, massive rubber pontoons that measured 33 feet long and 8 feet wide when fully inflated. But here was the revolutionary part. When deflated and rolled up, each float was just 4 feet long and less than 4 feet in diameter. A single 6-ton Brockway truck could carry 2 of these floats, plus the steel treadway sections and saddles needed to create 30 feet of functioning bridge. Compare this to the German system. Their standard pontoon was solid, steel or wood, sturdy and reliable, but each one required a dedicated heavy trailer for transport. A German pontoon company might stretch for miles along a road, vulnerable to air attack, impossible to conceal, and taking hours just to move into position. The American system could be transported by ordinary trucks, hidden in forests, and deployed with stunning speed. The creation of these pneumatic pontoons hadn't come from some brilliant stroke of military genius, but from the unglamorous reality of industrial problem-solving. In 1942, as American forces prepared for amphibious operations, engineers recognized a simple truth. Steel pontoons were too heavy, too slow to deploy, and required too much specialized equipment. What if, they asked, pontoons could be made of rubber, inflated on site, and supported by standardized steel treadways that any truck could carry? The result was tested extensively on American rivers, from the wide Missouri to the swift-flowing Susquehanna. Engineers discovered something remarkable. These rubber pontoons, when properly inflated to the correct pressure, could support extraordinary weight. A single M2 treadway bridge, supported by pneumatic floats spaced just 12 feet apart, could carry 40-ton Sherman tanks, heavy artillery pieces, and endless streams of trucks. The rubber absorbed shock, flexed with the current, and proved far more resistant to damage than anyone expected. Small arms fire might puncture a float, but each pontoon was divided into multiple air chambers. Even with several chambers deflated, the bridge remained functional. By early 1945, American engineers had perfected the system. Each pneumatic float came with its own inflation equipment, powered by Leroy compressors mounted on GMC trucks. A skilled crew could inflate a pontoon in under 15 minutes. The steel treadways, each 15 feet long, with raised edges forming dual tracks for vehicles, connected with simple pins. No welding, no complex assembly, just mechanical connections that worked even in darkness, even under fire. German intelligence had observed all of this. They'd seen these bridges in France, watched American engineers assemble them across the Moselle, the Saar, even smaller tributaries of the Rhine itself. But they'd made a fatal assumption. They believed these were temporary expedients, bridges that would be replaced by proper steel structures as soon as possible. They never imagined that the Americans would trust these rubber pontoons for the most important river crossing of the war. The man who would prove them wrong was Lieutenant General George S. Patton, commander of the U.S. Third Army. Patton had been racing across France and Germany with one singular obsession: beat British Field Marshal Bernard Montgomery across the Rhine. Montgomery, meticulous and cautious, was planning Operation Plunder, a massive, set-piece crossing for late March that would involve over 1 million troops, 5,000 artillery pieces, and an airborne assault larger than D-Day itself. It would be methodical, overwhelming, and according to Montgomery, inevitable. Patton found the entire concept offensive. While Montgomery prepared his grand operation, Patton's forces reached the Rhine in early March and immediately began probing for weakness. He found it near the towns of Oppenheim and Nierstein, small communities roughly 15 kilometers south of Mainz. The terrain here was favorable, with high ground on the western bank providing excellent observation and artillery positions. More importantly, German resistance appeared thin, disorganized, exhausted from months of retreat. On March 21st, Patton met with his chief engineer, Brigadier General John Conklin, and laid out his audacious plan. They would cross the Rhine that very night, more than 24 hours before Montgomery's massive operation. There would be no preliminary bombardment to alert the enemy, no weeks of preparation. Just assault boats to get infantry across, followed immediately by the engineers with their pneumatic pontoons and treadway sections. Conklin assured Patton it could be done. The 249th Engineer Combat Battalion, along with supporting units, had been training for exactly this scenario. They had over 90 pneumatic floats ready, enough steel treadway sections to span the Rhine multiple times, and most critically, they had speed. Conklin estimated they could have a functioning bridge across the river in 12 to 15 hours, maybe less if everything went smoothly. Patton called his superior, General Omar Bradley, and received perhaps the most perfect order any aggressive commander could hope for. Take the Rhine on the run. No elaborate planning, no coordination with other armies, just go. Bradley understood what Patton intended: to steal Montgomery's thunder and prove that American audacity could accomplish what British caution required weeks to prepare. But for this audacity to work, everything depended on the engineers and their supposedly inadequate rubber pontoons. The 249th Engineer Combat Battalion was commanded by Colonel John K. Addison, a West Point graduate who'd led his men through the Battle of the Bulge just months earlier. His soldiers were veterans, exhausted but experienced, and they understood the magnitude of what they were about to attempt. On the afternoon of March 22nd, Addison assembled his company commanders and laid out the operation. Company K of the 5th Infantry Division's 11th Regiment would cross first in assault boats, securing the eastern bank. Once they established a foothold, the engineers would move. Their mission: construct a 366-metre pontoon bridge from Nierstein on the western bank to the eastern shore near Trèbes. Completion time: before dawn. Speed was everything. The longer they took, the more time German artillery would have to target them. The engineers began moving their equipment to the riverbank as darkness fell. Each Brockway truck carried its carefully organised load: 2 rolled-up pneumatic floats, 2 steel saddles to connect the floats to the treadways, 4 15-foot treadway sections. Behind them came the Leroy compressor trucks, the power utility boats with outboard motors for manoeuvring pontoons into position, and the specialised equipment needed for anchoring the bridge against the Rhine's powerful current. Across the river, Obergefreiter Hartmann and his fellow soldiers listened to the distant sounds of activity on the western bank. They could hear engines, the occasional shout, the sounds of an army preparing for something. But in the darkness, they couldn't see the details. They expected the Americans to wait, to mass their forces, to begin with a massive artillery barrage that would give defenders hours of warning. That's how river crossings worked. That's how they'd always worked. At precisely 2200 hours, 10 o'clock in the evening, the first American assault boats slipped into the Rhine. Soldiers of Company K paddled through the moonlit water, expecting German fire at any moment. But the eastern bank remained eerily quiet. The boats grounded on the far shore, and infantrymen scrambled up the bank, weapons ready. Still nothing. The Germans, thinly spread and exhausted, simply hadn't expected an assault without preparatory bombardment. Within 30 minutes, Company K had established a secure perimeter on the eastern bank. Radio calls went back across the river. The landing zone was clear. Engineers could begin. This was the moment everything hinged on. If the German assessment of American pontoon bridges was correct, if those rubber floats really were inadequate for serious military use, the entire operation would bog down. The infantry would be stranded, vulnerable, cut off once German reinforcements arrived. But if the American engineers were right, if their pneumatic pontoons and treadway system could perform as promised, then in a matter of hours, Patton's entire Third Army could pour across the Rhine, exploiting German weakness before they could react. Colonel Addison gave the order. His engineers, who'd trained for this moment on rivers across France and Belgium, began their work. The first Brockway trucks backed down to the water's edge. Crews unloaded the rolled pneumatic floats, connecting them to the inflation equipment. The Leroy compressors roared to life, and slowly, almost magically in the moonlight, the flat rubber rolls began to inflate, expanding into massive 33-foot-long pontoons. The Germans had assumed these would be fragile, easily damaged. But the engineers handled them with practiced confidence. Each float was constructed of multiple layers of rubberized fabric, reinforced at stress points, and divided into separate air chambers. Even if enemy fire punctured one chamber, the others would keep the pontoon afloat. The inflation took just minutes per float, far faster than maneuvering a heavy steel pontoon into position. As each pneumatic float reached full inflation, work crews attached the steel saddles, U-shaped brackets that connected the float to the treadway sections. Then came the most critical part, floating each assembled section into position. Using the power utility boats, small wooden craft with outboard motors, engineers guided each pontoon and treadway unit into the Rhine, connecting them one by one to form a growing bridge extending from the western bank. The current was swift, just as German planners had anticipated. But the engineers had trained for this. They'd practiced on the fast-flowing Meuse River in Belgium, learning how to angle sections against the current, how to use temporary anchors, how to keep the bridge aligned even as the river tried to push it downstream. The rubber, pontoons, flexible and buoyant, absorbed the river's force rather than fighting it. A rigid steel structure might have buckled under the strain. The pneumatic system bent, flexed, and held. By midnight, the bridge extended nearly a quarter of the way across the Rhine. On the eastern bank, infantrymen watched in amazement as the structure grew steadily toward them. Back on the western bank, more trucks arrived, carrying additional pontoons, more treadway sections, supplies for the final assembly. Patton himself arrived, standing on the high ground overlooking the crossing site, binoculars pressed to his eyes. He watched his engineers work with an almost paternal pride. This was it. This was the moment that would end the war in the West. Around 1 o'clock in the morning, the first German shells began to fall. Artillery observers on the eastern bank had finally realized what was happening and called for fire. Explosions erupted in the Rhine, sending up geysers of water that drenched the engineers working frantically on their floating bridge. But the German fire was sporadic, uncoordinated. The defenders had expected crossings at Mainz, 10 kilometers to the north. They'd positioned their heaviest guns there, registered their fields of fire there. This crossing at Nierstein caught them completely unprepared. More critically, the German gunners couldn't believe what they were seeing. Through their optics, in the uncertain moonlight, they watched what appeared to be a bridge materializing out of nothing. Where were the massive steel pontoons? Where were the hours of preparation, the vulnerable build-up that should have given them time to mass their fire? The reports radioing back to division headquarters sounded almost panicked. The Americans were using some kind of inflatable bridge, and it was being assembled at impossible speed. Hauptmann Friedrich Weber commanded the nearest German artillery battery, 4 88mm guns positioned 3 kilometers inland. His orders had been clear: destroy any American bridging attempts. But when the reports came in, he initially didn't believe them. Rubber pontoons, supporting heavy military equipment, across the Rhine? It had to be a reconnaissance party, a feint to draw fire away from the real crossing. He ordered a few ranging shots, but held back his main fire, convinced the actual assault would come elsewhere. That decision would haunt him. By the time Weber realized this was the main effort, the American bridge was already halfway across the Rhine, and his battery found itself receiving counter-battery fire from American artillery on the western bank. The high ground Patton had selected provided perfect observation. American forward observers could see every German gun flash and immediately call in devastating, accurate fire. Weber's battery managed to fire perhaps 20 shells before American 155mm rounds began falling around their positions, forcing them to displace. The engineers working on the bridge barely paused. They'd expected German fire. In fact, they'd trained specifically for working under bombardment. The bridge design itself was remarkably resilient. When a German shell landed close to one pontoon section, shrapnel tore through the rubber, deflating 2 of the float's air chambers. The engineers immediately moved to that section with portable pumps and patches. Within 15 minutes, they'd sealed the punctures and re-inflated the chambers. The bridge never stopped growing. Private First Class Robert Shelado, a combat engineer from Rhode Island, worked through that night inflating and positioning pontoons. Years later, he would recall the surreal quality of the moment. We were building this bridge under moonlight, explosions going off around us, and the whole time I kept thinking about how the Germans probably thought we were crazy. These rubber boats, holding up steel roadways, carrying what would eventually be thousands of tons of equipment. If someone had told me a year earlier that we'd cross the Rhine on inflated pontoons, I'd have thought they were pulling my leg. By 3 o'clock in the morning, the bridge had reached the 3/4 mark. The eastern bank was now clearly visible, and infantrymen from Company K waded into the shallows to help guide the final sections into place. The connection between pontoon and treadway, pontoon and shore, required precise alignment. Too much stress on any single joint could cause failure, but the American system, tested and refined over months of combat engineering, worked flawlessly. The steel treadways, each with their raised dual tracks, locked together with simple pins that could be installed even with cold, wet hands. No complex tools required, no welding, nothing that couldn't be done in darkness under fire. This was democratic engineering at its finest, designed so that any trained soldier could assemble it, maintain it, repair it. Compare this to the German pontoon systems, which required specialized crews, specific tools, and hours of preparation. At 04:30 in the morning, just 6.5 hours after the first pontoon entered the water, the final treadway section locked into place on the eastern bank. The bridge was complete. 366 meters of floating roadway, supported entirely by inflatable rubber pontoons that German intelligence had dismissed as inadequate. Colonel Addison walked the length of the bridge, testing each connection, checking the anchoring. Everything held solid. But Patton wasn't satisfied with just completion. He wanted proof, dramatic proof, that would silence any doubts. At 0500 hours, as the first light of dawn began to break over the Rhine, he ordered a Sherman tank forward. Engineers and infantrymen held their breath as the 30-ton vehicle rolled onto the bridge. The pneumatic floats compressed slightly under the weight, the treadways flexed, but the structure held. The tank drove steadily across, its tracks gripping the steel surface, reached the eastern bank, and kept going into Germany. Behind it came another tank, then another, then trucks, artillery pieces, ammunition carriers, an endless stream of American military power flowing across what was supposed to be Germany's impregnable barrier. The bridge, built in less than 11 hours with equipment the Germans had mocked, was not just holding, it was thriving, handling loads that would have challenged a permanent steel structure. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. As morning fully broke on March 23rd, German commanders along the Rhine began to grasp the catastrophe unfolding before them. Radio reports from the Nierstein sector described an impossible situation. American forces were pouring across the Rhine in division strength, and they were doing it without a conventional bridge. Intelligence officers scrambled to understand what they were seeing. Aerial reconnaissance, when it could penetrate American air superiority, brought back photographs that seemed to defy reason. General Lieutenant Hans Schmidt, commanding the local defense sector, wrote in his log that morning, "The Americans have constructed a bridge at Nierstein using inflatable components we had previously assessed as suitable only for minor obstacles. Our intelligence evaluation was catastrophically incorrect. The bridge is supporting heavy armor and appears entirely functional. We lack the artillery concentration to destroy it, and American air superiority prevents our bombers from reaching the target." The psychological impact on German defenders was devastating. For weeks, they'd been told to hold the Rhine, that the river would buy them time, that crossing such an obstacle would take the Allies days of preparation and create vulnerable choke points that German forces could counterattack. Instead, they watched American trucks simply drive down to the river, unload rubber boats, blow them up like children's pool toys, and create a functioning military bridge in less time than it took to cook breakfast. Unteroffizier Ernst Vogel, captured the next day, expressed the demoralization perfectly during his interrogation. They crossed the Rhine like it was a creek. We were told the Rhine would stop them, that our engineers said the American pontoons couldn't handle serious loads. Then we watched 40-ton tanks drive across on rubber boats. What else had we been lied to about? But the story of the pneumatic pontoons wasn't just about a single bridge at Nierstein. Within hours of that first crossing, additional bridges were going up at Oppenheim, just downstream. By the evening of March 23rd, American engineers had constructed 2 complete bridges across the Rhine, both using the same pneumatic pontoon and treadway system. Upstream, at Boppard and Sankt Gore, more crossings were underway. The speed and flexibility of the M2 treadway system allowed American forces to cross at multiple points simultaneously, something German defensive doctrine had never anticipated. Traditional steel pontoon bridges required massive logistics trains, took days to assemble, and created obvious targets. The American system could be transported by ordinary trucks, assembled in hours, and redeployed if necessary. German artillery trying to target these bridges found themselves facing a nightmare. By the time they'd registered their guns on one crossing point, another bridge would be functional kilometers away. On March 24th, just 2 days after the initial Nierstein crossing, over 60,000 American troops had crossed the Rhine. Behind them came the vehicles: trucks, tanks, artillery pieces, ammunition carriers, fuel tankers, mobile kitchens, field hospitals, everything an army needed to sustain offensive operations. All of this flowed across. Bridges that German intelligence had assured the High Command were inadequate for serious military use. The numbers tell the story of German miscalculation. A traditional steel pontoon bridge, by German calculations, required approximately 16 hours to construct across the Rhine under ideal conditions, with no enemy interference. The American pneumatic system accomplished the same task in 11 hours, while under sporadic artillery fire. German steel pontoons required specialized heavy transport vehicles, limiting where bridges could be built. American pneumatic pontoons could be carried by standard 6-ton trucks, allowing crossings at any point with basic road access. Most devastatingly, German doctrine assumed that destroying a pontoon bridge required only a few well-placed artillery rounds or bombs. Hit the pontoons, collapse the structure. But the American pneumatic system proved remarkably resilient. Multiple air chambers meant that even punctured floats remained partially functional. The flexible nature of rubber absorbed shock better than rigid steel, and repairs could be made on the spot with patches and portable pumps, equipment every engineer unit carried as standard. Technical Sergeant Anthony Caruso, an engineer who worked on the Nierstein Bridge, remembered one incident that perfectly illustrated this resilience. On the second day, a German fighter managed to strafe the bridge. Bullets stitched right through 3 pontoons. We could hear the air hissing out. Everyone figured we'd have to halt traffic, maybe even close the bridge for repairs. But the pontoons had multiple chambers, see? So even with some deflated, they still had enough buoyancy. We kept traffic moving while a repair crew worked from a boat underneath. Patched the holes, pumped them back up, and the bridge never stopped operating. Try doing that with a steel pontoon that's been hit. The engineering accomplishment at Nierstein caught the attention of Supreme Headquarters Allied Expeditionary Force. General Dwight D. Eisenhower himself sent a message to Patton. The Rhine crossing has exceeded all expectations. Your engineers have demonstrated the effectiveness of American engineering doctrine and equipment. Congratulations on this achievement. But Patton, never one for excessive modesty, wanted to make a point not just militarily but symbolically. On March 23rd, he arrived at the Nierstein Bridge in his command jeep, cameras following. Halfway across, he ordered the vehicle to stop. What happened next became one of the war's most famous photographs. Patton climbed out of his jeep, walked to the edge of the bridge, unzipped his trousers, and urinated into the Rhine. The gesture was crude, quintessentially Patton, and absolutely deliberate. He wanted the Germans to know, wanted the world to know, that their sacred river, their 2,000-year barrier, meant nothing to American engineering and American determination. When he reached the eastern bank, Patton bent down, scooped up a handful of German soil, and proclaimed, "Thus, William the Conqueror," imitating the Norman king's legendary gesture when landing in England. The symbolism wasn't lost on anyone. The Rhine, which Julius Caesar had declared the natural boundary of Roman civilization, which had stopped Napoleon's armies, which had been Germany's psychological defense as much as a physical one, had been crossed in a single night by rubber pontoons the Germans hadn't taken seriously. The message was clear. American industrial ingenuity had rendered German military doctrine obsolete. Behind Patton's theatrical gestures lay a profound truth about the nature of modern warfare. The Germans had approached engineering with craftsmanship, creating beautiful, precisely engineered equipment that required skilled specialists to operate and maintain. The Americans had approached the same problems with mass production philosophy. Make it simple, make it reliable, make thousands of them, and train ordinary soldiers to use them. The pneumatic pontoon epitomized this philosophy. Yes, a German steel pontoon was more robust in isolation, but an American pneumatic float could be produced faster, transported easier, deployed quicker, and repaired simpler. When you multiplied these advantages across an entire army, across hundreds of river crossings, the cumulative effect was overwhelming. Germany could field a handful of perfect steel pontoon bridges, America could field hundreds of good enough pneumatic bridges, and in total war, quantity had its own quality. By March 26, just 4 days after the initial crossing, American engineers had moved over 60,000 military vehicles across the Rhine at Nierstein and Oppenheim. The two bridges operated around the clock, with traffic control maintaining a steady flow in both directions. Wounded soldiers were evacuated west, while ammunition and supplies flowed east. Mobile repair units crossed to establish forward maintenance facilities. Fuel tankers kept the advancing armored divisions supplied. The bridges became highways, arteries feeding the American advance into the heart of Germany. German attempts to destroy these bridges grew increasingly desperate and increasingly futile. Artillery fire proved ineffective against the distributed, flexible structure. The Luftwaffe, already decimated by Allied air superiority, managed only a handful of attacks. On March 25, a German fighter bomber penetrated American defenses and dropped a bomb near the Oppenheim Bridge. It exploded 15 meters from the structure, sending up a massive plume of water. When the spray cleared, the bridge was still there, pontoons bobbing in the waves, completely functional. A captured German pilot, shot down later that day, expressed the hopelessness his comrades felt. We were told to destroy the American bridges. But they're not like our bridges. They're not solid targets you can hit and collapse. Flexible, they're multiple, and they fix damage faster than we can create it. It's like trying to destroy a river by bombing water. The contrast with Montgomery's massive Operation Plunder, which launched on March 23, couldn't have been more stark. Montgomery's operation involved over 1 million troops, 5,000 artillery pieces, firing 4 hours of preparatory bombardment, and massive airborne drops. It was thoroughly planned, methodically executed, and ultimately successful. But it took weeks of preparation and announced itself with such obvious build-up that German defenders had days to prepare. Patton's crossing at Nierstein involved no preliminary bombardment, minimal preparation time, and achieved complete surprise. By the time Montgomery's forces crossed the Rhine in strength, Patton's army was already 15 kilometers into Germany, expanding their bridgehead and racing toward Frankfurt. The pneumatic pontoons, dismissed by German intelligence, had accomplished what massive British preparation required weeks to achieve. The human stories from the Rhine crossing capture the magnitude of this engineering triumph. Lieutenant James Morrison, a platoon leader in the 5th Infantry Division, crossed on the Nierstein Bridge at dawn on March 23. He remembered looking down at the river rushing past beneath the treadways, seeing the rubber pontoons flexing with the current, and thinking, "This is crazy. This is brilliant. This is America." Sergeant First Class William Henderson, an engineer, recalled the exhaustion mixed with pride. "We worked 36 hours straight building and maintaining those bridges. Guys were falling asleep standing up, but we knew we were doing something special. The Germans had spent months fortifying the Rhine, and we crossed it in one night with rubber boats and American know-how. When I saw that first tank cross, when I felt the bridge hold solid under 40 tons of steel, I knew we'd won. Not just won, won the whole damn war." For the German forces defending the Rhine, the pneumatic pontoon bridges represented something more than military defeat. They represented the complete failure of their intelligence apparatus, their engineering doctrine, and their understanding of American capabilities. Throughout the war, German propaganda had emphasized American materialism, portraying them as wealthy but soft, capable of producing quantity but not quality. The pneumatic pontoons shattered this narrative. Here was American engineering that was both simple and sophisticated, mass-produced yet highly effective. Oberst Wilhelm Brandt, a German engineer officer captured after the Rhine crossings, was brought to see the American bridges. His post-war interrogation report captures his assessment. The American pontoon bridge system represents a fundamental difference in engineering philosophy. We Germans sought perfection in individual components. The Americans sought sufficiency in mass production. For warfare, especially modern mechanized warfare, their approach proved superior. A perfect bridge that takes a week to build is inferior to an adequate bridge built in 12 hours. The 249th Engineer Combat Battalion received recognition for their achievement. The bridge they'd constructed in 18 hours, under fire, across one of Europe's major rivers, became legendary in U.S. Army engineer history. Decades later, a memorial would be erected at the exact spot where their bridge touched the western bank at Nierstein, commemorating not just military victory but engineering excellence. But perhaps the most telling evidence of the pneumatic pontoon's success came from an unexpected source. After the war, when Allied intelligence officers examined captured German engineering documents, they found plans dated April 1945, just weeks before Germany's surrender, for a German copy of the American pneumatic pontoon system. Even in their final days, German engineers had recognized the superiority of the American design and were attempting to replicate it. The irony was profound. For years, German intelligence had dismissed American pneumatic pontoons as inadequate. By the time they recognized their mistake, it was far too late. The Rhine had been crossed, the heartland of Germany lay open to Allied armies, and the Third Reich was collapsing. The paper pontoons, as some German soldiers derisively called them, had accomplished what centuries of military planners had considered nearly impossible, turning the Rhine from a barrier into a highway. The morning of March 27, 1945, brought a sight that would have seemed impossible just 5 days earlier. From a hilltop observation post overlooking the Rhine, an American logistics officer counted vehicles crossing the pontoon bridges at Nierstein and Oppenheim. In a single hour, he tallied 137 trucks, 23 tanks, 18 artillery pieces, and 42 other military vehicles, all flowing eastward into Germany on bridges supported by inflatable rubber pontoons. By the end of that first week, more than 60,000 military vehicles had crossed the Rhine at Patton's bridgeheads. The logistical achievement was staggering. Each vehicle represented tons of fuel, ammunition, food, medical supplies, and spare parts that needed to cross as well. The pneumatic pontoon bridges handled it all, operating 24 hours a day, with engineer maintenance crews working in shifts to keep the structures functional. The strategic implications rippled across the entire European theatre. With the Rhine barrier breached in multiple locations, German defensive planning collapsed. Field Marshal Gerd von Rundstedt, overall commander of German forces in the West, had based his entire strategy on holding the Rhine until spring, buying time to consolidate defences and potentially negotiate a separate peace with the Western Allies. The rapid American crossings, accomplished with such surprising ease, shattered that hope. In Berlin, the news reached Adolf Hitler's bunker on March 23. According to accounts from surviving staff officers, Hitler initially refused to believe the reports. American forces crossing the Rhine in strength after just one night, using inflatable bridges? It had to be Allied propaganda, exaggerated reports meant to spread panic. But as confirmations arrived from multiple sources, as Luftwaffe reconnaissance photographs showed the unmistakable pontoon bridges stretching across the sacred river, Hitler's rage turned to despair. Joseph Goebbels, Hitler's propaganda minister, wrote in his diary on March 25, "The situation in the West has become catastrophic. The Americans have crossed the Rhine at multiple points, using a bridge system our intelligence failed to take seriously. Our last natural barrier is gone, breached by rubber boats our experts dismissed as inadequate. This failure represents not just military defeat, but intellectual bankruptcy." The human cost of the Rhine crossings, while significant, was far lower than pre-operation estimates. Allied planners had anticipated casualties in the thousands, expecting fierce German resistance and costly fighting to establish bridgeheads. Instead, the surprise achieved at Nierstein and Oppenheim, combined with the speed of the pontoon bridge construction, resulted in remarkably light losses. The 5th Infantry Division reported fewer than 40 casualties during the initial crossing and bridge construction. The 249th Engineer Combat Battalion lost 3 men killed and 11 wounded during the entire operation. Compare this to the Battle of Remagen, where the unexpected capture of an intact bridge 2 weeks earlier had cost hundreds of American lives to hold against German counterattacks. The pneumatic pontoon bridges at Nierstein allowed American forces to cross so quickly and in such strength that German counterattacks never materialized in force. By the time German commanders organized a response, the bridgehead was too large, too well supplied, and too heavily reinforced to dislodge. For the engineers who built and maintained these bridges, the success brought both pride and exhaustion. Staff Sergeant Marcus Powell, who worked 48 consecutive hours during the initial crossing and subsequent bridge maintenance, recalled the physical toll. "We were running on coffee, cigarettes, and adrenaline. Guys would finish inflating a pontoon, then just collapse on the riverbank for 10 minutes before getting up to do another one. But we couldn't stop. Every hour we delayed was an hour the infantry had to wait for supplies, for reinforcements, for ammunition. We knew lives depended on us keeping those bridges operational. The maintenance of the pneumatic pontoon bridges required constant vigilance. The Rhine's current was powerful, carrying debris downstream that could damage the structures. Fallen trees, pieces of destroyed German equipment, even the occasional dead horse swept down from upstream battles, all posed threats. Engineer crews stationed along the bridges worked with poles and boats to deflect debris, guide it between pontoons, and ensure nothing struck the vulnerable connection points between treadways. Weather added another challenge. Spring rains increased the Rhine's flow, raising water levels and strengthening currents. The flexible nature of the pneumatic pontoons proved advantageous here as well. Unlike rigid structures that might have buckled under increased water pressure, the rubber floats simply rose with the water level, maintaining their buoyancy and structural integrity. Engineers adjusted anchor lines and monitoring inflation pressure, but the bridges remained operational through conditions that would have closed traditional pontoon structures. The German response evolved from disbelief, desperate improvisation. On March 28, German frogmen attempted to plant explosives on the Oppenheim Bridge's pontoons. They swam downstream in darkness, carrying limpet mines designed to attach to the rubber floats. But American security had anticipated this threat. Patrol boats with searchlights swept the river constantly, and machine gun nests on both banks maintained overlapping fields of fire. The frogmen were detected before reaching the bridge, and only 2 of the 6 swimmers survived to be captured. The captured frogmen, during interrogation, revealed that German commanders had initially assumed the rubber pontoons would be easily sabotaged. Cut a few pontoons, they reasoned, and the entire bridge would collapse. But reconnaissance had revealed the multiple air chamber design, meaning even damaged pontoons remained partially functional. The Germans simply lacked the resources to mount the kind of sustained sabotage campaign that might have succeeded. On March 30th, 1 week after the initial Nierstein crossing, General Eisenhower himself visited the pontoon bridges. He walked the length of the Nierstein structure, stopping to talk with engineer crews, examining the pneumatic floats and steel treadways. An aide recorded Eisenhower's comments. "This bridge, built in 18 hours with equipment our enemy dismissed as inadequate, represents everything that makes American forces effective: practical engineering, rapid execution, and the courage to try something our enemies thought impossible." Eisenhower ordered that lessons learned from the Rhine crossings be immediately disseminated throughout Allied forces. The pneumatic pontoon system had proven itself beyond any doubt, and future river crossings would emphasize speed and flexibility over elaborate preparation. The success at Nierstein validated American engineering doctrine and provided a template for operations throughout the remainder of the war. The broader strategic impact of the Rhine crossings became apparent within days. With multiple Allied armies across the river, German defensive coherence collapsed entirely. American armored divisions raced eastward, some advancing 50 kilometers in a single day. German units, unable to establish new defensive lines without the Rhine barrier to anchor them, found themselves constantly outflanked, constantly retreating, increasingly demoralized. On April 1st, American forces from the Remagen and Oppenheim bridgeheads linked up, encircling the entire Ruhr industrial region and trapping Field Marshal Walter Model's Army Group B, over 300,000 German soldiers. This catastrophic encirclement was made possible by the speed with which American forces had crossed the Rhine and exploited their bridgeheads. Had the crossings taken days longer, had bridge construction proceeded at the slower pace German intelligence anticipated, Model might have withdrawn his forces and continued organized resistance. Instead, Model found himself trapped. On April 21st, recognizing the hopelessness of his situation, he released his soldiers from their oaths of allegiance and shot himself rather than surrender. The commander who'd been ordered to hold the Rhine had watched his entire defensive strategy collapse when American engineers accomplished in hours what German doctrine insisted required days. The fate of the pneumatic pontoon bridges themselves varied. The original Nierstein Bridge operated continuously until mid-April, when permanent bridge structures and the general Allied advance made it unnecessary. Engineers then disassembled the bridge, loaded the pneumatic floats and treadway sections back onto trucks, and moved them forward to support crossings of the Weser and Elbe rivers. The equipment proved as reusable as it was deployable, another advantage over heavier, more specialized German systems. Some pontoons showed remarkable durability. Technical records indicate that several pneumatic floats used at Nierstein had previously supported bridges across the Moselle, the Saar, and smaller rivers in France and Belgium. Despite months of use, multiple inflations and deflations, and occasional combat damage, These floats remained serviceable through April 1945. The simplicity of their construction, rubber fabric reinforced at stress points, made field repairs straightforward and extended operational life far beyond what German intelligence had predicted. The 249th Engineer Combat Battalion continued operations until Germany's surrender on May 8, 1945. They built bridges, cleared obstacles, established supply routes, and performed the unglamorous but essential work that kept armies moving. But their 18-hour construction of the Nierstein Bridge remained their crowning achievement, the operation that proved American engineering excellence under combat conditions. After the war ended, military analysts on both sides examined the Rhine crossings to understand what had happened and why. German after-action reports revealed a consistent pattern of intelligence failure. Multiple reports had noted American use of pneumatic pontoons, but analysts had consistently underestimated their capabilities. This failure stemmed from fundamental cultural biases about engineering quality versus quantity, craftsmanship versus mass production. A captured German engineering manual from 1944 contained a section on Allied bridging equipment. The entry on American pneumatic pontoons included the dismissive assessment. Rubber construction indicates emergency nature of equipment, unlikely to support sustained heavy traffic or resist combat damage effectively. This single sentence, reflecting deep-seated assumptions about proper engineering, cost Germany dearly when those supposedly inadequate rubber pontoons carried an entire army across the Rhine. American engineers, by contrast, had approached the problem from a completely different direction. They didn't ask, "What's the best possible pontoon?" They asked, "What pontoon can we build quickly, transport easily, deploy rapidly, and produce in the thousands?" The pneumatic float answered all these questions brilliantly, even if it lacked the impressive solidity of a steel pontoon. In war, the adequate solution available immediately beats the perfect solution that arrives too late. The Rhine crossings also highlighted another American advantage: the integration of logistics with tactical operations. German forces had always separated logistics from combat arms, viewing supply as a support function rather than a combat multiplier. American doctrine treated logistics as warfare's foundation. Those pneumatic pontoons, carried forward by ordinary truck companies, maintained by standard engineer battalions, represented logistics as a weapon system. The ability to cross any river quickly meant armies could maintain momentum, exploit breakthroughs, and keep enemies constantly off balance. In the decades after World War II, the pneumatic pontoon became a case study in military engineering programs worldwide. The basic concept, lightweight, inflatable supports for temporary bridges, influenced bridge design through the Cold War and beyond. Modern military bridging systems still incorporate inflatable components, though made with advanced materials far superior to 1945 rubber. But the fundamental principle, that flexibility and rapid deployment often matter more than maximum load capacity, traces directly back to the Rhine crossings of March 1945. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe. For the soldiers who lived through those March days, the memories remained vivid for the rest of their lives. Robert Schelado, the last surviving veteran of the Nierstein crossing, returned to Germany in 2017 for the dedication of a memorial at the exact spot where the bridge touched the western bank. Then, 93 years old, Schelado stood before a crowd of Germans and Americans, describing the night his battalion built a bridge the enemy thought impossible. "We were just doing our jobs," Schelado said that day. "But looking back, I realize we were part of something bigger. We proved that American ingenuity, American determination, and American industrial might could overcome any obstacle. The Germans had the Rhine, 2,000 years of history telling them it couldn't be crossed. We had rubber boats and 18 hours, and we won." The memorial at Nierstein features a section of actual pneumatic pontoon, preserved and displayed alongside photographs from the March 1945 crossing. The inscription, in both English and German, reads, "Here, soldiers of the 249th Engineer Combat Battalion constructed a bridge in 18 hours that helped end World War II. Their achievement demonstrated that courage, ingenuity, and practical engineering can overcome any barrier." Standing at that memorial today, you can still see the Rhine flowing past, powerful and wide, the natural barrier that once seemed unconquerable. It's difficult to imagine that 75 years ago, inflatable rubber pontoons supported by steel treadways carried an entire army across this river, accomplishing in hours what military planners thought would take days. But the memorial's pontoon, faded but still intact, provides physical proof of what American engineers achieved. The story of the Rhine crossing resonates because it captures something essential about the American way of war. Not the most elegant solution, not the most technically impressive, but the most practical, the most producible, and ultimately, the most effective. The Germans built beautiful steel pontoons that required specialists to deploy. The Americans built rubber pontoons that any soldier could inflate and use. When the test came, in the cold waters of the Rhine in March 1945, the simple American solution defeated German complexity. For the engineers of the 249th Battalion and their counterparts in other engineer units, the Rhine crossing validated everything they'd trained for. Combat engineering wasn't glamorous. Nobody wrote songs about inflating pontoons or positioning treadways. But without those bridges, Patton's audacious crossing would have stalled, American momentum would have been lost, and the war in Europe might have dragged on for months longer, costing thousands more lives on both sides. In the grand narrative of World War II, the pneumatic pontoon bridges of the Rhine crossing represent a larger truth, that modern warfare rewards industrial efficiency, logistical excellence, and practical innovation as much as martial valor. The German soldier, who fought bravely but lacked supplies, lost to the American soldier, adequately supplied. The German engineer who crafted perfect equipment slowly lost to the American engineer who produced good equipment quickly. The German commander who relied on barriers lost to the American commander who brought the tools to overcome any obstacle. The Rhine, for 2 millennia, had been Germany's shield. Roman legions stopped at its banks. Medieval armies treated it as the boundary of the known world. Napoleon's forces found it a formidable obstacle, but in March 1945, American engineers with rubber pontoons and steel treadways transformed it from a barrier into a highway, from Germany's last hope into just another river to cross on the road to Berlin. Obergefreiter Klaus Hartmann, the German soldier who'd watched the Western Bank on the night of March 22nd, survived the war. In a post-war interview conducted by American historians, he reflected on that night. "I was supposed to watch for American bridging equipment, the big steel pontoons we'd been trained to recognize. Instead, they used rubber boats I didn't understand were dangerous. By the time I realized what was happening, the bridge was half built. I radioed my officers, but they didn't believe me. How could rubber boats support tanks? But they did. Everything we'd been taught, everything we'd been promised about the Rhine, all of it was wrong." Hartmann's story captures the essential tragedy of the German defensive strategy. They'd prepared for the war they expected, defending against the equipment they anticipated, following the doctrine they'd always known. The Americans fought the war that was actually happening, using equipment that worked regardless of whether it was impressive, following doctrine that prioritized results over tradition. When these two approaches collided on the Rhine, the outcome was never in doubt. The German soldiers who mocked American paper pontoons learned a harsh lesson that March. Those despised rubber boats, those supposedly inadequate inflatable floats, carried the army that would conquer the Third Reich. They held tanks, carried artillery, supported supply trucks, and never failed in their essential mission. They were the embodiment of American industrial philosophy. Make it simple, make it reliable, make enough of them, and win the war. In the end, the story of the Rhine crossing isn't just about bridges and engineering. It's about the collision between two different ways of thinking about war, about technology, about what matters when nations fight for survival. The Germans valued perfection, craftsmanship, the beauty of well-engineered solutions. The Americans valued sufficiency, mass production, the pragmatism of solutions that worked, even if they weren't elegant. On the Rhine in March 1945, pragmatism defeated perfection. Inflatable pontoons defeated steel construction. American industrial might, channeled through practical engineering, accomplished what German military tradition could not prevent. And in those cold, fast-flowing waters, supported by rubber boats, the enemy never took seriously. An army crossed a river that was supposed to be uncrossable, and in crossing it, sealed the fate of the Third Reich. The morning after the Nierstein Bridge opened, as American trucks rolled endlessly across the Rhine, a German prisoner stood watching from a detention area on the Western Bank. An American guard, seeing his expression, asked what he was thinking. The German soldier replied simply, "We should have taken your rubber boats more seriously." That sentence, bitter with recognition and regret, epitomizes the entire story. The Germans laughed at American paper pontoons, dismissed them as inadequate, assumed their Rhine fortress was safe. And then, in 11 remarkable hours, American engineers proved that sometimes the most unimpressive equipment, wielded with skill and determination, can achieve the impossible. The Rhine had stood as Germany's barrier for 2,000 years. But American rubber pontoons, mass-produced and democratically designed, turned it into just another river to cross on the road to victory. And in that transformation, in that achievement of practical engineering over historical precedent, lay one of World War II's most profound lessons, that wars are won not just by courage or strategy, but by the industrial and engineering capacity to turn practical ideas into battlefield reality faster and more effectively than your enemy ever imagined possible. The Rhine had stood as Germany's barrier for 2,000 years, but American rubber pontoons, mass-produced and democratically designed, turned it into just another river to cross on the road to victory. And in that transformation, in that achievement of practical engineering over historical precedent, lay one of World War II's most profound lessons, that wars are won not just by courage or strategy, but by the industrial and engineering capacity to turn practical ideas into battlefield reality faster and more effectively than your enemy ever imagined possible. The morning after the Nierstein Bridge opened, as American trucks rolled endlessly across the Rhine, a German prisoner stood watching from a detention area on the western bank. An American guard, seeing his expression, asked what he was thinking. The German soldier replied simply, "We should have taken your rubber boats more seriously." That sentence, bitter with recognition and regret, epitomizes the entire story. The Germans laughed at American paper pontoons, dismissed them as inadequate, assumed their Rhine fortress was safe. And then, in 11 remarkable hours, American engineers proved that sometimes the most unimpressive equipment, wielded with skill and determination, can achieve the impossible. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe. The morning of November 8, 1943, a Japanese convoy steams through the Philippine Sea. 14 cargo ships arranged in 2 neat columns, flanked by 4 destroyer escorts. The night is moonless, the visibility near zero. The convoy commander, a veteran of 2 years of Pacific warfare, believes his ships are safe. Submarines, after all, hunt by periscope during daylight. At night, submerged and blind, they're helpless. Surface visibility in this weather extends perhaps 2,000 yards on a clear night, maybe less in this rain. The convoy maintains radio silence, changes course every 20 minutes, according to doctrine, and runs without lights. Every precaution has been taken, every rule followed. Yet 20 miles away, USS Pargo already knows exactly where they are. Not from visual sighting, not from periscope observation, but from a rotating antenna mounted on her bridge, sending invisible pulses into the darkness and receiving back precise echoes of distance, bearing, and speed. The Japanese don't know this technology exists on submarines. When their ships begin exploding at midnight, they'll assume it was luck. Terrible, impossible luck. By dawn, 6 of those 14 cargo ships will be on the bottom, and the surviving convoy commander will file a report describing an attack that, by every principle of submarine warfare he understands, should have been impossible. This weapon, this revolutionary technology that the Japanese Navy never detected on American submarines, would sink approximately 1,200 Japanese ships over 3 years of warfare. It would transform night from a sanctuary into a killing field, and it would do something even more psychologically devastating. It would make Japanese naval officers question reality itself, because the attacks they were experiencing violated every tactical assumption, every training principle, every understood limitation of submarine warfare. How do you defend against an enemy who can see you when you cannot see them? How do you evade detection when the detection method is completely unknown to you? If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The roots of this technological revolution reach back to 1941, when the United States Navy recognized a fundamental problem with submarine warfare. Submarines were designed to be invisible, but that invisibility came with a crippling limitation. A submerged submarine was effectively blind. Periscopes provided limited daytime vision, perhaps 5 to 7 miles in perfect conditions, far less at night or in weather. Sonar could detect ships, but only at close range, and with significant uncertainty about bearing and distance. This meant that finding enemy ships required either incredible luck, precise intelligence about convoy routes, or dangerous surface operations where the submarine was exposed and vulnerable. Pre-war doctrine emphasized patient, defensive operations. Submarines would patrol likely shipping lanes, wait for targets to appear within periscope range, and attack from submerged positions. This was safe, stealthy, and almost completely ineffective against a skilled enemy who zigzagged, changed course frequently, and travelled in convoys with destroyer escorts. The solution began with an improbable technology: radar. The use of radio waves to detect distant objects, by sending pulses of electromagnetic energy and measuring the echoes that bounced back. British and American researchers had developed radar for aircraft detection in the late 1930s, creating systems that could spot incoming bombers at ranges of 50 to 100 miles. By 1940, shipboard radar was being installed on cruisers and destroyers, giving surface fleets the ability to detect enemy vessels beyond visual range. But submarines presented unique challenges. Radar equipment in 1941 was large, heavy, and power-hungry. It required substantial antennas, complex electronics, and trained operators. Submarines had limited space, limited power generation, and crews already stretched thin operating the boat's systems. Early submarine radar, designated SD, was primitive. Installed on American submarines beginning in 1941, it could detect aircraft at roughly 6 to 10 miles, giving submarines warning to dive before being spotted. But SD radar was almost useless for surface search. It lacked directional capability, couldn't provide accurate bearings, and had insufficient range to be tactically useful for finding enemy ships. This changed in mid-1942. Naval Research Laboratories, working with MIT's Radiation Laboratory, developed a revolutionary new radar system specifically designed for submarine operations. It was designated SJ radar, and it would transform submarine warfare as profoundly as the torpedo itself. SJ radar operated at 10 centimeters wavelength, what's called S-band frequency. This was significantly higher frequency than earlier radars, which meant smaller antennas, better resolution, and more accurate target information. The entire system was compact enough to fit through submarine hatches for installation, crucial because submarines couldn't be extensively modified without dry dock time the Navy couldn't afford to spare. The radar antenna mounted on a retractable mast that could be raised while surfaced, rotating to scan 360 degrees of horizon. In the submarine's conning tower, an operator watched a plan position indicator, or PPI scope, a circular display where radar contacts appeared as bright blips. The operator could measure bearing and distance with remarkable precision. A large ship might be detected at 20 miles or more, a destroyer at 15 miles. Even a small patrol boat could be picked up at 10 miles in good conditions. Ranges that were utterly impossible with visual observation at night. More importantly, SJ radar was directional. The submarine commander knew not just that a ship was out there, but exactly where it was, how fast it was moving, and in which direction. This transformed submarine tactics from educated guesses into calculated science. By early 1943, SJ radar was being installed on virtually every fleet submarine in the Pacific. The technology itself was classified at the highest levels. Submarine commanders were briefed extensively on radar capabilities, but also on security. They were never to mention radar in radio communications unless using specific codes. If attacked or forced to abandon ship, radar equipment was to be destroyed immediately. The Japanese were not to discover this capability, and for an astonishingly long time, they didn't. The Imperial Japanese Navy had its own radar development program. Japanese scientists had been experimenting with radio detection since the mid-1930s. By 1942, Japan had deployed some early warning radar systems for air defense, particularly around major bases and the home islands. But Japanese radar development faced severe institutional obstacles. The Army and Navy refused to cooperate, each developing separate systems that often duplicated efforts and never shared advances. Japanese universities lacked the academic freedom that fostered innovation in American and British research programs. Technical personnel were difficult to recruit. One German professor visiting Japan in 1938 observed that Japanese universities resembled senior high schools, with predetermined curricula that stifled creative research. Perhaps most critically, Japanese naval leadership did not prioritize radar for surface vessels. The doctrine that had served them so well in the first year of the war, the emphasis on night combat, torpedo attacks, and superior optics, seemed to be working. Why invest heavily in unproven electronics when Japanese lookouts, trained in exceptional night vision and equipped with excellent binoculars, could spot enemy ships at night far better than any technology? By 1943, some Japanese warships carried radar, primitive air search sets that could detect high-flying aircraft. But these systems were unreliable, poorly understood by crews, and often kept shut down to avoid providing Allied direction-finding equipment with a signal to home on. Japanese doctrine actually required radar silence until enemy aircraft were within 10 miles, which eliminated radar's primary advantage of early warning. Surface search radar, the type that could detect ships at sea, was virtually non-existent in the Imperial Japanese Navy until late 1944. Even then, only a handful of warships received the equipment, and Japanese destroyers, the vessels that might escort convoys, almost never had it. More significantly, Japanese submarines, the vessels that might have warned of American submarine capabilities through captured equipment or survivor interviews, never received submarine-mounted surface search radar at all. This created an intelligence blind spot of staggering proportions. The Japanese Navy, fighting a desperate war against American submarines that were systematically destroying their merchant marine, never understood that every single one of those submarines could see in the dark. The asymmetry was profound. An American submarine commander, surfaced at night, could detect a Japanese convoy at ranges of 15 to 20 miles, sometimes more. He could track multiple ships simultaneously, plot their courses, calculate their speeds, and maneuver into optimal attack position, all while the convoy remained completely unaware of his presence. Then, having positioned his submarine with mathematical precision, he could charge into the convoy at high speed, surface torpedoes at point-blank range from multiple targets, and escape in the confusion, while Japanese escorts searched blindly for an enemy they couldn't see and couldn't imagine existed. From the Japanese perspective, these attacks were incomprehensible. Submarine attacks were supposed to come during the day, from periscope depth, with torpedoes that gave some warning of approach. Night attacks were considered nearly impossible, a desperate gamble where the submarine had no more visibility than the target. Yet these attacks were happening with disturbing frequency and devastating accuracy. Ships were being sunk in the darkest hours of night, in weather conditions where visual detection should have been impossible, with a precision that suggested the submarines knew exactly where every ship in the convoy was located. Japanese naval intelligence speculated wildly. Perhaps American submarines had superior optics, some kind of advanced night vision capability. Perhaps they were using sound detection, listening for the noise of ship propellers through hydrophones, and attacking based on audio cues. Perhaps, some theorists suggested, the Americans had developed a form of magnetic detection that could sense the presence of steel hulls at distance. None of these theories came close to the truth. The reality was simpler and more devastating. The Americans could see them, and they couldn't see back. Consider the tactical revolution this created. Before radar, submarine warfare was largely opportunistic. A submarine would patrol a likely shipping route and hope that a target appeared within detection range. If the submarine was surfaced, this might mean visual range of perhaps 10 miles in daylight, far less at night. If submerged, it meant periscope range of 5 to 7 miles at best. Attack opportunities were rare, and many required hours of maneuvering to achieve a firing position. With SJ radar, everything changed. A submarine could detect convoys at ranges of 20 miles or more, often before the convoy's lookouts could possibly spot the submarine. This gave the submarine commander enormous tactical flexibility. He could track the convoy's course and speed while remaining undetected, plot an intercept course, and position his submarine ahead of the convoy's path. Then, as the convoy approached, he could surface, use radar to confirm positions, and attack from optimal angles. The entire process was calculable, predictable, almost scientific in its precision. More importantly, radar enabled night surface attacks to become standard tactics rather than desperate gambles. Before radar, a submarine commander attacking at night was essentially blind, relying on brief glimpses of ship silhouettes against a slightly lighter sky, guessing at ranges and bearings. With radar, that same commander had precise, continuous tracking of every ship in the convoy. He knew where the escorts were. He knew where the cargo ships were. He knew which ships were large, valuable targets and which were smaller auxiliaries. He could select his targets methodically, fire his torpedoes with confidence, and evade with precision. The American submarine force, which had struggled through 18 months of near-total ineffectiveness due to defective torpedoes, suddenly became the most lethal naval weapon in the Pacific theater. And the Japanese never understood why. Submarine commanders began developing attack techniques that exploited radar's capabilities. One particularly effective method was the end-around. A submarine would detect a convoy at long range, then run on the surface at high speed, using its 16 to 18 knot surface speed to race ahead of the convoy and position itself in front of the convoy's path. Once in position, the submarine would wait, submerge to periscope depth as the convoy approached, or remain surfaced if confidence in position was high, then attack as the convoy arrived. Radar made this possible by providing continuous tracking of the convoy's position, course, and speed, even when the protector submarine was running at high speed and could not use the periscope. Another technique was the coordinated attack. Multiple submarines operating in the same area would share radar contact information, vectoring each other towards the convoy. While one submarine might distract escorts or be detected, the others, using radar to track the chaos, would slip in undetected and deliver devastating attacks. These wolfpack tactics, borrowed from German U-boat operations in the Atlantic, but perfected with radar in the Pacific, created situations where Japanese convoys might face simultaneous attacks from multiple directions, coordinated with a precision that seemed almost supernatural to the defenders. The psychological impact on Japanese merchant marine crews and naval officers was severe. Ship captains began to report attacks that violated every known principle of submarine warfare. Convoys were being ambushed in the darkest nights, in the worst weather, with an accuracy that seemed to indicate the submarines had exact advance knowledge of routes and schedules. Some officers theorized that American submarines must be receiving intelligence from spies in Japanese ports, detailed information about departure times and routing. This was partially true. American code-breaking provided excellent intelligence about convoy schedules. But code-breaking couldn't explain how submarines found convoys in the vast Pacific Ocean, or how they maneuvered with such precision in total darkness. The truth was simpler and more terrifying. The submarines didn't need spies in ports because they had radar at sea. By mid-1943, the cumulative effect of radar-equipped submarines became impossible to ignore. Japanese shipping losses, which had been substantial throughout 1942 and early 1943, suddenly exploded. In 1942, American submarines had sunk approximately 500,000 tons of Japanese shipping. In 1943, with working torpedoes and effective radar, that number jumped to nearly 1.8 million tons. But it was in 1944 that the true devastation became apparent. With torpedo problems fully resolved, radar systems refined through operational experience, and aggressive new tactics fully implemented, American submarines achieved what can only be described as systematic annihilation of the Japanese merchant marine. In about 520 war patrols during 1944, American submarines sank over 600 Japanese merchant ships, totaling approximately 2.7 million tons, more ships than in the first 25 months of war combined. Japanese commodity imports, the lifeblood of the island empire, plunged from 16.4 million tons to 10 million tons in a single year. The submarines were strangling Japan's economy, and radar was the invisible hand tightening the noose. Consider what these numbers meant in human terms. 600. Merchant ships represented thousands of skilled merchant marine officers and crew members, men with families, men who had trained for years in their profession, men whose experience could not be replaced. Every ship sunk was also a catastrophic loss of cargo: oil tankers carrying fuel for Japanese aircraft, freighters loaded with raw materials for war production, transports packed with troops being shifted between garrison islands, rice ships bringing food to feed the population. Every single one of these vessels was critical to Japan's ability to continue fighting. And every single one that went to the bottom made the empire weaker, more desperate, more vulnerable. The Japanese tried to respond. Convoy escort procedures were tightened. Destroyers were assigned to protect merchant ships, though never in sufficient numbers. Routing was changed more frequently. Ships began to hug coastlines where shallow water might protect them from submarine attack, though this made them vulnerable to mines and aircraft. But none of these measures addressed the fundamental problem. The Japanese couldn't defend against an advantage they didn't know existed. If Japanese naval intelligence had understood that American submarines carried sophisticated radar, countermeasures might have been possible. Japanese warships could have been equipped with radar detectors that would warn of submarine radar emissions. Convoys could have been routed to avoid areas where radar was most effective. Escorts could have used their own primitive radar to search for surfaced submarines. But because Japanese intelligence never discovered or understood the scope of American submarine radar capabilities, none of these countermeasures were developed. The submarines continued their slaughter undetected, unhindered, and almost unopposed. There's a bitter irony in how the secret was maintained. American submarines were occasionally sunk, about 52 boats over the course of the war. A casualty rate of 22% that made submarine duty the most dangerous service in the American military. When these submarines were lost, any radar equipment aboard sank with them. Japanese forces occasionally captured submarine crew members, survivors of sunk boats who became prisoners of war. These men were interrogated extensively, questioned about tactics, training, and equipment. But submarine crews had been thoroughly briefed on security. They knew that revealing radar capabilities would endanger other submarines. Some simply refused to discuss technical matters. Others provided misleading information, describing primitive SD air search radar, but never mentioning the far more capable SJ surface search system. Japanese interrogators, lacking the technical background to ask the right questions, never penetrated this security. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The transformation in American submarine effectiveness between 1942 and 1944 represents one of the most dramatic combat turnarounds in naval history. It resulted from fixing the catastrophic torpedo problems that had plagued the first 18 months of war. Problems where torpedoes ran too deep, exploded prematurely, or failed to explode at all. It resulted from aggressive new tactics pioneered by commanders like Dudley Marsh-Morton, who proved that submarines could successfully attack on the surface at night. And it resulted from radar, the technological advantage that made aggressive tactics possible by giving submarines the ability to see when their enemies were blind. The strategic consequences rippled across the Pacific War. By late 1944, Japan's merchant marine was approaching total collapse. Ships that had survived 2, 3, or 4 years of war were finally being sunk. Experienced crews were dead or scattered across so many undermanned ships that efficiency plummeted. New construction, never sufficient to replace losses, was further hampered by Allied air attacks on Japanese shipyards and by growing shortages of steel and other raw materials. The Navy, desperate to maintain supply lines, began pressing fishing boats, coastal freighters, and even small private vessels into service as cargo carriers. Many of these were under 1,000 tons, barely capable of crossing open ocean, certainly not fast enough to evade submarines or well built enough to survive torpedo hits. They sank in enormous numbers, often with total loss of crew. Japanese industry, starved for raw materials, began shutting down production lines. Aircraft factories ran short of aluminum. Steel mills lacked iron ore. Ammunition plants ran low on explosives. The synthetic fuel plants that Japan had built to reduce dependence on imported oil couldn't get the coal they needed to operate. By early 1945, Japanese industrial production had fallen to a fraction of 1941 levels, not because factories had been bombed, though some had, but because submarines had cut off the flow of materials. The Japanese military found itself unable to move forces where they were needed. Troops stationed in China, Southeast Asia, and scattered Pacific islands were effectively stranded. Moving them required ships that no longer existed or couldn't be risked in waters patrolled by submarines. Reinforcing garrison islands became almost impossible. The climactic battles of Iwo Jima and Okinawa were fought with the defenders unable to receive significant reinforcements or supplies because submarines controlled the sea lanes. Even the home islands faced genuine hunger. Japan, with over 70 million people crowded onto islands that could not feed themselves, depended on rice imports from Korea, Taiwan, and Southeast Asia. As submarine warfare intensified, these shipments dwindled, then nearly stopped. By mid-1945, civilian rations in Japanese cities had fallen below subsistence levels. People were genuinely starving, not from American bombs, but from American submarines that had severed the lifelines keeping the population alive. And through all of this, the Japanese Navy never understood the fundamental reason for their shipping catastrophe. Reports from convoy commanders described impossible attacks, submarines that appeared to know exact convoy positions, attacks delivered with precision in conditions where such precision should have been impossible. Intelligence officers speculated about enhanced American training, about superior periscopes, about new kinds of torpedoes that must surely explain the devastating accuracy. None came close to the truth. The Americans had radar, and that changed everything. The question that haunted Japanese naval planning by 1945 was both simple and unanswerable. How do you defend shipping when the enemy can find your convoys with near certainty, can attack with scientific precision, and then disappear before your escorts can respond? Some Japanese officers proposed abandoning convoy routes entirely, having ships sail independently and depend on luck to avoid submarines. This was tried occasionally and proved even more disastrous, as isolated ships were even more vulnerable to patient submarine commanders who could stalk them for hours before attacking. Others suggested running supplies by submarine rather than surface ships, on the theory that submarines couldn't sink what they couldn't find. Japan attempted this with some limited success, but Japanese submarines were far fewer in number than the cargo ships they were meant to replace, and their carrying capacity was minimal compared to even a small freighter. By the final months of the war, Japanese merchant shipping had been so thoroughly destroyed that the submarine campaign effectively ended, not because the submarines stopped operating, but because there were simply no more significant targets to sink. The few remaining Japanese ships huddled in port, unwilling to venture into waters they knew were patrolled by submarines they couldn't detect and couldn't fight. This is the story of an invisible weapon. Not invisible because it was secret, though its specific capabilities were highly classified. Invisible because the enemy never detected its presence, never understood how it worked, never developed countermeasures, and never even knew it was the primary reason their shipping was being destroyed. The Japanese Navy fought World War II in the Pacific against submarines that could see them clearly while remaining themselves unseen. It was warfare as asymmetric as cavalry against machine guns, battleships against aircraft carriers, warriors with swords against warriors with rifles. The side with the technological advantage won because their advantage was so complete, so overwhelming, that the other side couldn't even comprehend what they were facing. By the time Japan surrendered in August 1945, American submarines had sunk approximately 1,200 Japanese merchant ships and 200 warships. They had destroyed more than half of Japan's merchant marine tonnage. They had killed tens of thousands of merchant marine crew members, soldiers being transported between garrisons, and sailors serving on warships. And they had done this while operating as a tiny percentage of American naval forces, 52 boats, and 16,000 men at sea, constituting less than 2% of the Navy, but achieving more than 50% of Japanese shipping destruction. The legacy of submarine radar extends far beyond World War II statistics. Modern submarines, whether diesel-electric boats patrolling coastal waters or nuclear-powered monsters prowling deep ocean, depend on sensors that trace their lineage directly to SJ radar. The principle remains unchanged. Detect the enemy before they detect you. Maneuver with precision, while they maneuver blindly, and strike with calculated accuracy, while they fight shadows. Electronic warfare, the science of detecting, jamming, and exploiting enemy sensors, has its roots in the radar campaigns of World War II. Today's naval forces invest billions in stealth technologies designed to minimize radar signatures, in electronic countermeasures designed to confuse enemy radars, and in increasingly sophisticated sensors designed to penetrate enemy stealth and countermeasures. This technological arms race began in the Pacific when American submarines used radar to find Japanese ships that had no idea they were being electronically tracked. But perhaps the most important legacy is strategic. The American submarine campaign demonstrated that economic warfare, systematically destroying an enemy's ability to sustain military operations, can be as decisive as destroying their military forces directly. Japan lost World War II not primarily because its army and navy were defeated, in battle, though they certainly were, but because its economy was strangled by submarines that cut the arteries feeding the empire. Modern strategic thinking about blockades, about interdiction campaigns, about targeting logistics rather than combat forces, all derive from lessons learned in the Pacific Submarine War. Military planners understand that in modern warfare, destroying an enemy's supply chain can be more effective than destroying their frontline units. Cut off fuel, ammunition, food, and replacement parts, and even the finest military forces become ineffective. This principle, proven by radar-equipped submarines hunting Japanese merchant ships in dark Pacific waters, remains central to military doctrine worldwide. There's a human dimension to this story that statistics and tactical analysis can obscure. Consider the experience of an American submarine crew on a typical war patrol in 1944. 70 to 80 men, living in a steel tube, roughly 300 feet long and 27 feet wide at its widest point. They would depart from Pearl Harbor, Fremantle, or another forward base and steam for weeks toward their assigned patrol area, often waters near Japan, the Philippines, or the South China Sea, deep in enemy-controlled territory. The living conditions were barely tolerable. The interior of a submarine at sea could reach temperatures above 100 degrees Fahrenheit. The air grew progressively more foul as carbon dioxide built up and oxygen was consumed. Men slept in bunks, stacked 3 high with barely 18 inches between them. Some slept on cots strung between torpedoes. Privacy was non-existent. The entire crew shared perhaps 2 or 3 toilets, and even those sometimes couldn't be flushed when the submarine was deep or under attack. Food was monotonous. Fresh provisions lasted perhaps a week, after which meals consisted of canned goods and dried stores that became increasingly unappetizing as the weeks passed. Water was strictly rationed. Showers, when allowed at all, might be limited to 30 seconds of water to wet down, then 30 seconds to rinse off. Some submarines went weeks without anyone being able to shower properly. The smell inside the boat, a mixture of diesel fuel, unwashed bodies, cooking odors, and the tang of battery acid, became so pervasive that crew members stopped noticing it, though they could smell it on themselves for days after returning to port. And every moment of every day, they lived with the knowledge that their survival depended on remaining undetected. A single mistake, one careless noise, one moment of bad luck, and destroyers would be overhead dropping depth charges. The experience of being depth charged was terrifying beyond description. The submarine would crash dive, racing to get below the thermocline layer where sonar had difficulty tracking, then rigging for silent running. Every unnecessary piece of equipment would be shut off. Men would stop moving. Conversations ceased. The only sounds would be the creaking of the hull under pressure and the distant propellers of destroyers hunting above. Then the depth charges would begin. Each explosion created a hammer blow that shook the entire boat. Light bulbs would shatter, gauges would crack. Cork insulation would rain down from the overhead. Depth charges set to explode at the submarine's depth would create pressure waves that compressed the hull, forcing it to groan and pop as metal flexed beyond design tolerances. Men would stand frozen, listening to their boat being tortured, wondering if the next explosion would be the one that cracked the pressure hull and sent tons of seawater flooding in at lethal pressure. Some depth charge attacks lasted hours. The submarine, unable to surface, unable to run, unable to fight back, could only sit silently and endure while destroyers above methodically worked a search pattern, dropping charges in an attempt to bracket the submarine and deliver a pars, killing blow. Battery power would dwindle. The air would grow more toxic. Men would begin to experience splitting headaches from carbon dioxide buildup. Some would lose consciousness, and through it all, they had to remain absolutely silent, because any noise might give away their position and bring another pattern of depth charges down upon them. Yet these men, subjected to these conditions patrol after patrol, achieved extraordinary things. The casualty rate was 22%, meaning roughly 1 in 5 submariners who went to war never came home. 52 submarines were lost with all hands, boats that left port on patrol and simply never returned. In some cases, we know what happened. Depth charges that finally cracked the hull, mines that detonated beneath the boat, torpedoes from enemy submarines, aircraft attacks while surfaced. In other cases, submarines simply vanished, and we can only speculate about their fate. USS Wahoo, commanded by Dudley Mush Morton, the legendary submarine captain who had pioneered aggressive surface attacks, was lost in October 1943 in La Perouse Strait. Japanese records eventually revealed that aircraft had spotted the submarine and delivered a fatal attack. Morton, who had sunk more than 20 Japanese ships in less than a year of command, never knew that his boat had been detected. The entire crew, 80 men, died with him. USS Tang, commanded by Richard O'Kane, Morton's former executive officer and perhaps the most successful submarine commander of the war, was lost in October 1944 under circumstances that might be the cruelest irony in submarine warfare history. After sinking 13 ships on its 5th war patrol, a record-setting performance, Tang fired its last torpedo at a Japanese transport. The torpedo malfunctioned, circled back, and struck Tang. The submarine sank in less than a minute. 9 men, including O'Kane, survived and were captured. The rest of the crew, 78 men, went down with the boat. USS Grunion was lost in July 1942 off the coast of Alaska, with all 70 crew members. The submarine wasn't found until 2006, when wreckage was located showing that Grunion had been sunk by return fire from a Japanese patrol boat it was attacking. The submarine had been missing for 64 years before families finally learned what had happened. These losses, and the dozens of others like them, represented not just strategic setbacks, but profound human tragedies. Every submarine carried 70 to 80 men who had families, who had lives before the war, who had dreams for after the war. Every boat lost meant 70 to 80 families who received telegrams informing them that their son, husband, father, or brother was missing and presumed lost. In many cases, families never learned exactly what happened, only that the submarine failed to return from patrol. Yet the submariners kept volunteering. After every loss, after every patrol that came back with stories of depth, charge attacks, and near misses, men continued to sign up for submarine duty. Some were motivated by patriotism, the genuine belief that they were fighting to win the war and save lives by shortening the conflict. Others were drawn by the extra pay that submarine duty offered, money that could support families or build savings for after the war. Some simply found that they were good at this particular form of warfare, that they had the temperament to remain calm under pressure, to endure weeks of boredom punctuated by moments of terror, to function effectively in an environment that drove many men to psychological breakdown. And they were effective. The submariners of World War II, comprising less than 2% of the Navy's personnel, accounted for more than 55% of Japanese shipping losses. They sank 8 aircraft carriers, 1 battleship, 11 cruisers, and over 200 other warships. Destroyed Japan's ability to wage war more effectively than the strategic bombing campaign, more effectively than the island-hopping campaign, more effectively than any other single American military effort in the Pacific. The Japanese perspective on this campaign deserves consideration as well. For Japanese merchant marine officers, the war became a nightmare of impossible choices. Every voyage carried the risk of submarine attack. Convoys offered some protection through destroyer escorts, but convoys also moved slowly and were easier to detect than independent ships. Ships sailing alone could make better speed and theoretically be harder to find, but if detected, they had no protection at all. Japanese merchant captains developed superstitions and rituals. Some believed that certain routes were cursed, that ships traveling those routes never returned. Others believed that maintaining strict radio silence protected them, not understanding that radio emissions weren't how submarines were finding them. Some captains tried unpredictable routing, changing course randomly every few minutes, hoping that erratic movement might confuse submarine commanders. What they didn't know was that radar tracking made their movements predictable, regardless of course changes. The doctrine of aggressive counterattack, charging toward the direction of torpedo launches and dropping depth charges in the area where the submarine was thought to be, occasionally worked, but more often resulted in destroying empty ocean, while the submarine, having tracked the destroyer's approach with radar, simply moved to a different position and prepared another attack. Japanese naval intelligence struggled to understand the pattern of losses. Reports from convoy commanders were studied extensively. Charts were prepared showing where attacks occurred, what times of day they happened, what weather conditions prevailed, whether convoys or independent ships were more vulnerable. Patterns emerged, but the patterns were misleading. Attacks seemed to cluster in certain areas, leading to the conclusion that submarines must be concentrated there, when the reality was that submarines were distributed throughout Japanese-controlled waters and simply attacking whichever convoys they found. Attacks occurred overwhelmingly at night, leading to theories about American submarine doctrine favoring night operations, when the reality was that radar made night operations far more effective than daytime attacks. Large, slow-moving ships seemed disproportionately targeted, suggesting that submarines were selecting victims based on visual observation of size, when the reality was that radar returns from large ships were stronger and easier to track. Every conclusion Japanese intelligence drew was based on the false assumption that American submarines were operating with the same limitations as Japanese submarines. The possibility that American submarines had a fundamental technological advantage. 1. That allowed them to detect ships beyond visual range regardless of weather or lighting conditions, was considered but never confirmed. Japanese radar experts knew that radar could theoretically be mounted on submarines. They had themselves experimented with submarine radar for air search purposes, but the technical challenges of mounting effective surface search radar on submarines, given the equipment's size, power requirements, and the need for careful antenna installation, seemed prohibitive. Japanese intelligence estimated that if American submarines did have radar, it would be primitive air search equipment similar to what Japanese submarines carried, useful for detecting approaching aircraft, but of limited value for finding ships. The possibility that American submarines carried sophisticated surface search radar comparable to what cruisers and destroyers used never seriously entered Japanese strategic calculations. By late 1944, some Japanese signals, intelligence units had detected radar emissions in areas where submarine attacks subsequently occurred. These reports were analyzed, but the analysis was hampered by lack of understanding about radar technology and by the assumption that radar emissions must be coming from American surface ships or aircraft, not submarines. The idea that submarines might be radiating powerful radar signals while hunting in enemy-controlled waters seemed tactically absurd. Surely the radar emissions would alert Japanese forces and draw attacks. None of these countermeasures were implemented because the fundamental capability was never discovered. Japanese anti-submarine warfare continued to operate on pre-radar assumptions about submarine limitations, assuming that submarines hunted primarily by periscope or sound and were effectively blind at night. Japanese convoy tactics, routing procedures, escort doctrines, all were designed to counter an enemy that didn't exist, while the actual enemy, radar-equipped submarines operating with nearly perfect information about convoy positions, continued their methodical destruction of Japanese shipping. By August 1945, when Japan surrendered, the merchant marine that had begun the war with approximately 6 million tons of shipping had been reduced to less than 1.5 million tons still afloat. American submarines accounted for the majority of those losses. The oil didn't flow from the Dutch East Indies. The raw materials stayed in China and Southeast Asia. The food didn't reach the home islands. The troops couldn't be moved where they were needed. An empire built on conquest and maintained by sea power simply ran out of everything it needed to continue fighting. The ultimate irony is that Japan had developed some radar technology. Japanese scientists understood the principles. Japanese engineers could build radar systems. Japanese factories produced radar equipment. But institutional failures, inter-service, rivalries, cultural resistance to abandoning traditional methods, and fundamental misunderstanding of how radar could revolutionize warfare meant that Japan never deployed the technology where it was most needed. They never put effective radar on merchant ships. They never equipped destroyers with sophisticated search radars. They never developed doctrine for using radar in anti-submarine warfare. And most critically, they never imagined that their enemy had solved all these problems and deployed radar in the most unlikely place of all, on submarines. This is the story of 1,200 Japanese ships that vanished into dark Pacific waters, sunk by an enemy that could see them when they couldn't see back. It's the story of technological advantage so complete that the losing side never even understood what weapon was being used against them. It's the story of American submariners who endured brutal conditions, faced terrifying dangers, and achieved strategic victory through a combination of courage, innovation, and technology that their enemy never detected. The men who served in submarines during World War II rarely discussed their experiences after returning home. The missions were classified, the losses were painful, the memories of depth charges, of ships sinking, of weeks submerged in toxic air. These weren't stories that translated easily to peacetime life. Many submariners dealt with what would now be recognized as post-traumatic stress, though the term didn't exist and treatment wasn't available. They had nightmares about drowning, about being trapped in sinking steel tubes, about the faces of men who didn't come back. They carried guilt about surviving when so many didn't. And they carried the knowledge of what they had accomplished, the certain understanding that their efforts had shortened the war and saved lives, even as those efforts required taking lives in ways that haunted them. The Japanese merchant marine officers and crew members, who survived the war, carried their own scars. They had watched ships they served on being sunk. They had lost friends and shipmates. They had survived in lifeboats for days or weeks, watching other survivors die from exposure, dehydration, or injuries. Some had been aboard multiple ships that were torpedoed, experiencing the terror of submarine attack again and again. Their stories, told in Japanese accounts published after the war, describe a growing sense of helplessness, the understanding that no amount of courage or seamanship could protect against an enemy that struck invisibly from the darkness. The technological legacy of submarine radar extends into the present day. Modern submarines, whether American Virginia-class boats, Russian Akula-class boats, Chinese Type 093 boats, or smaller diesel-electric submarines operated by dozens of nations, all carry sophisticated radar systems that trace their lineage to the SJ radar of World War II. The frequencies have changed. The antennas are more sophisticated. The signal processing is done by computers rather than human operators watching cathode ray tubes. But the principle remains unchanged. Detect the enemy before they detect you, and use that information advantage to achieve tactical superiority. Electronic warfare, the science of using, exploiting, and denying electromagnetic spectrum dominance, has become one of the most important fields in modern military technology. Ships, aircraft, and ground forces all carry equipment designed to detect enemy radar, to jam enemy communications, to spoof enemy sensors, and to operate effectively in electromagnetically contested environments. This field, which now represents billions of dollars in annual military spending and employs tens of thousands of specialists, began with lessons learned from submarine radar in the Pacific War. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.